A buck boost converter is required whenever we need both a step up capability under some operating conditions as well as a step down capability under a different set of operating conditions from the same converter. So in this video we look at a basic buck boost converter topology and go through its operating principles, steady state analysis, and look at the average models. Finally, we'll also analyze the waveforms valid in both the buck and the boost modes of operation, which will eventually lead to the design methods in a later video. Here is a schematic of the buck boost converter. The input Vin on the left hand side, the output Vo on the right hand side. Also notice how the output polarity has been defined. The power pole comprising of the switch S1 and the diode D1 is connected between the input and the output as shown, and the switch S1, usually a MOSFET, is switched at high frequencies. The gate drive waveform is shown here. When Q is 1, the switch is on, and that is the DTS interval. When Q is 0, switch is turned off, and we will show that the diode gets forward biased, and that is the 1 minus D times TS interval. Now in this video we will stick to analysis only in the continuous current mode, CCM mode of operation. A few points about this topology before we get into the detailed analysis. First of all, it meets a basic requirement that it can provide both step up as well as step down capability depending on the operating duty ratio. Another important point is that with respect to the input ground, the output is really a negative value. Again, if you look at how we defined the polarity of Vo in this schematic, the positive is defined at the bottom and negative at the top. With this assignment of polarity, Vo is a positive number, but clearly with respect to the input ground, Vo is negative. Finally, the isolated version of the buck boost converter called as the flyback converter is a very popular topology at low power levels, less than 100 watts. Mainly due to the low parts count for an isolated converter. To understand the basic principle of operation, let's look at the equivalent circuits valid in the two sub-intervals, essentially the on interval DTS period and the off interval 1 minus DTS period. In the on interval, switch S1 is on. So this is the equivalent circuit valid in the on interval. Since S is on, this is the switch is a short circuit, input connected directly to the inductor. Now the voltage across the diode, we can see the cathode is at a potential of Vn and the anode is at a potential with respect to the ground of minus Vo. Therefore the diode is reverse biased by a large voltage of Vn plus Vo, and it is off, and therefore this is an open circuit here, and the capacitor is supporting the load. So again, from this equivalent circuit we can clearly see that VL, the voltage across the inductor during this sub interval, is the input voltage Vn, and because of the positive voltage the current IL rises and therefore the energy stored in the inductor increases. Simultaneously, the capacitor, as seen from the equivalent circuit, supports the full load current, and it is discharging, but we assume that and we actually designed such that the C is large enough to maintain the voltage almost constant during this interval as well as in the next interval. So essentially this leads to this small ripple approximation. Now at the end of the on interval, switch S1 is turned off, and since the inductor current has built to some positive value, now that will force a path through the capacitor and the output load resistance and complete through the diode D1. So this equivalent circuit is shown in this figure. Since S1 is off, this is open circuited, and the inductor current now completes through the capacitor current load current combination through the diode, which is shown as a short circuit in this equivalent circuit. So essentially the energy was stored in the inductor during the on interval, and that stored energy is partially released to the capacitor load combination during the off interval. So again, from the equivalent circuit, the VL, or the voltage across the inductor during the off interval, is minus Vo with this polarity of Vo, and therefore the inductor current due to the negative voltage begins to decrease, and the energy stored in the inductor also decreases, and this decrease in energy is what is being delivered to the output capacitor and to the load. During this interval, the capacitor current, again as defined here, is positive, and the capacitor stored charge increases during this interval. And once again, we assume that C is large enough that even with this charging current, the voltage remains almost constant. Also, notice that in the off interval, when the inductor current flows through the output capacitor and the load, the current direction is is in this direction, from the bottom to the top, and that is why we have VO to be of this polarity. Essentially, with respect to the input ground, the output voltage is a negative value. Next, let's derive the input-output relationship for a buck boost converter. So we'll start with our basic gate drive waveform Q, 1 and 0, defining the DTS and the 1 minus DTS intervals. And during this DTS interval, again looking at the equivalent circuit that we showed in the previous slide, VL was equal to Vn. Essentially, the switch connects the inductor directly to the input voltage, that is VL equals Vn. And during the off interval, the diode connects the inductor to the output voltage with this polarity. So VL switches between Vn and minus VO, and from this waveform we can derive the input-output relationship using the volt-second balance for the inductor voltage. So essentially we say that VL average is equal to 0 in steady state, and VL average is given by this expression. During the on interval, magnitude is Vn, the duration is DTS, and during the off interval, the value is minus VO, and the duration is 1 minus D times TS, and the sum is equal to 0. And if we collect the terms Vn and VO separately, Vn times D equals VO times 1 minus D, which gives us the basic relationship, which is for a buck boost, VO over Vn equals D over 1 minus D, where D is the operating duty ratio. So clearly for D less than 0.5, this expression gives comes out to be less than 1. Therefore, VO is less than Vn. That is a buck mode of operation. And for D greater than 0.5, this expression comes out to be more than 1. Therefore, VO is higher than Vn, or a boost mode of operation. The valid range of D is, of course, between 0 to 1 as indicated here. Now finally, we can also derive the input-output current relationship using the power balance, and since we have done this several times before, if VO over Vn is some value, then In over IO is the same expression due to the power balance. So essentially the ratio of input current to the output current is also D over 1 minus D. Now that we have looked at the schematics of the three basic DC-DC topologies, namely the buck, the boost, and the buck boost, let's look at their inductor voltage waveform, and this will help us explain in a different way why the step up as well as step down capability is possible in the buck boost converter and not in the buck and the boost. So if you look at the all the three waveforms are inductor voltage waveform VL, and they have similar looking square wave voltage waveforms, but the magnitudes in each interval would be very different among the three converters. In a buck, during the on interval it is the Vn minus VO, and during the off interval it is minus VO. Now it is this magnitude of Vn minus VO during the on interval that essentially requires the output voltage to be less than the input voltage, because we know that the off interval voltage is negative. Therefore the on interval should be a positive voltage waveform, and this Vn minus VO can be positive only if Vn is higher than VO. Therefore this is a step down or a buck operation, and only this is possible for any value of duty ratio. If you look at the boost converter, during the on interval the VL is Vn, and during the off interval it is Vn minus VO. Again, Vn is a positive value, and for VL average to be 0, we require this Vin minus VO to be a negative value, and this can be negative only if VO is higher than Vn, and this implies that this is a boost converter, and only step up is possible for any duty ratio, or VO has to be higher than Vn because of the requirement that Vn minus VO be negative. Whereas if you look at the buck boost, during the on interval it is Vn, during the off interval it is minus VO. So in neither of the on or the off interval, there is no requirement for Vn or VO to be higher or less than the other. Therefore, depending on the duty ratio, we can have both a step up as well as a step down operation. That is, VO can be higher or less than Vn, depending on the operating conditions. So if the on interval is higher than the off interval, then Vn has to be lower, and vice versa. So that's why, as shown here, for a buck boost, both step up and step down is possible. Getting back to the buck boost converter, let's look at the effect of some of the non-ideal components on the input-output voltage relationship. So in a previous slide, we derived under all ideal assumptions that VO over Vn is d over 1 minus d, and here is the plot of this ideal input-output voltage relationship. Essentially, this is d over 1 minus d plot, and under the yellow box, that corresponds to the buck mode of operation, with d varying from 0 to 0.5, and VO over Vn correspondingly goes from 0 to 1. So that's the buck mode of operation. For d higher than 0.5, we enter the boost mode of operation, and theoretically the VO over Vn should go all the way up to infinity at d equals 1. But we know that the non-ideal components would begin to dominate for higher values of d. In fact, it is the resistance of the inductor winding, the on-state resistances of the MOSFET, and the diode's forward drop. They begin to dominate at a higher duty ratio. And this is the plot when we consider the just the winding resistance of the inductor. So at low values of d, it is almost the same as the ideal relationship, but for d higher than around 0.7, it begins to deviate, and at high values of d, it is significantly different. And in particular, for d equals 1, there is no power transfer. VO over Vn goes all the way down to 0. Therefore, it is difficult to achieve large conversion ratios, for example, greater than 10, using the buck boost converter. We saw a similar situation for the boost converter as well. So if we do need a large conversion ratios, then either we need to use isolated converters with large transformer turns ratios, or have a cascaded multi-stage boost or a buck boost converter. Next, let's look at the average model of the buck boost converter. So here is the conventional way of drawing the buck boost schematic, and to get the average model, we know that we have to replace this power pole, essentially the switch diode combination, by its average model, which is nothing but an ideal transformer with the turns ratio equal to the operating duty ratio. Now, we can't certainly replace the power pole by the transformer in this schematic itself, but probably it is easier to visualize if you, as shown by this animation, just flip it to the right. So essentially, this is the same exact circuit. All we have done is we just flipped it so that we can easily replace this power pole by the transformer, and so this circuit becomes essentially as shown here. So here is the bipositional switch, and the output capacitor R combination is shown here, and the input is shown here. So essentially, this is the same exact circuit. We not changed anything, but it is probably easier to go from this circuit to its average model. So the average model is just take out this yellow box and replace that by the ideal transformer model, with the primary with the turns of 1 going to the what we call as voltage port. So that is shown here, VVP, and the current port is the secondary of the transformer, is now connected to this inductor, and so on. So just replace this yellow box by the transformer, we get the average model, and we call this as a full average model, and this is valid for both steady state analysis as well as any transient analysis. So this can be used for any purpose except those that involve obtaining switching frequency information, like the inductor currents switching ripple, or the switch voltage and current waveforms, and so on. But any average applications, whether it is steady state or transient, this full average model is applicable. We can simplify the full average model further to obtain the DC steady state average model, which of course is valid only for DC steady state analysis, and this is obtained as shown in this circuit by replacing all the inductors by short circuits and all the capacitors by open circuit. And there's also another small difference. If you notice the notation of the duty ratio, it is uppercase D here and lowercase d in the full average model. Essentially, the lowercase d includes all the DC values plus, for example, any perturbation signals, whereas the uppercase D denotes only the DC value at a given operating condition. We can use either of these two average models for example, deriving the input-output voltage or the current relationships, and for many other analysis. So, for example, if you look at the input-output voltage relationship, if we use so from this DC steady-state average model, we can see that VO is essentially the secondary voltage, and that is D times the primary voltage, which itself was VO plus Vn. So VO equals D times VO plus Vn, from which we directly get VO over Vn equals D over 1 minus D. Or if we use the full average model, again VO is equal to this VCP average, because VL average is 0 in steady state, and VCP average is again D times VO over plus Vn, leading to the same result. Or we can get the input-output current relationship again by looking at this DC average model. So essentially IN is a current that is indicated here, flows into the primary, and that by definition of transformer should be equal to D times IL. And IL is again doing a KCL at this node is equal to IO plus IN. Therefore IN over IO can be shown to be D over 1 minus D. Now these are same exact relationship that we derived from the switching model. The power of the average model is not just in deriving these steady state relationship, but in doing a transient analysis using the full average model, and also to derive the various transfer functions that are needed to do a controller design. Here is an example to show that the DC average models can significantly simplify problems related to DC steady state analysis. So in this example, we want to study the impact of this winding, the inductor windings series resistance, denoted by this R sub L, on the input-output voltage relationship. So on the right is the DC steady state average model corresponding to this case. So it is very it is same as the one that we saw in the previous slide, except that the inductor is not just a short circuit, but it is given by its winding resistance RL in this DC steady state model. So once we have this model, then for example IL, the secondary current is given by this voltage, which is D times VO plus Vn minus VO divided by this RL is the inductor current IL. Now if you look at the KCL at this node, the IL splits as this current IN and another current going as IO, but the current IN again by transformer relationship is simply D times this IL. Therefore the current going into the load resistance is 1 minus D times IL. So therefore VO is 1 minus D times IL times the resistance R, and substituting for IL from the first equation into the second, we get this expression. And if we collect all the VO terms and Vin terms separately, we get the third expression, which leads to the required relationship of VO over Vn under non-ideal situation, to be the original ideal expression d over 1 minus d times this extra term, which is r over r plus this RL series resistance over 1 minus d the whole squared. So if RL equals 0 as in the ideal case assumption, then this term vanishes, and what we have is the original expression d over 1 minus d corresponding to the ideal situation. Finally, let's look at some of the important waveforms of a buck-boost converter, both to get a much deeper understanding of the basic operating principle, as well as to come up with the design methods in a later video. In this slide, we are going to focus on the buck mode of operation, essentially for d less than 0.5. The first waveform is the input voltage Vin, which is a constant, and for the buck mode of operation, the output voltage Vo is always less than Vin as indicated here. The next waveform would be that of the inductor voltage waveform, which we have seen before while deriving the input-output voltage relationship. So VL is Vin during the on interval and minus Vo during the off interval, with the average being equal to 0. Now the inductor voltage waveform gives us the wave shape of the inductor current. So during the on interval, it is a rising waveform with a slope equal to Vin over L, and during the off interval, it is a falling waveform, again with slope equal to minus Vo over L. Now, so this is so there is a family of curves corresponding to different initial conditions that is possible for a given inductor voltage waveform. So the unique waveform that corresponds to the given operating condition is given by looking at the average current, for example. So the IL average, again by looking at a KCL at this node, average KCL is equal to IS1 plus ID1, all average values. IS1, since it is directly in series with the input voltage source, is IN, and ID1 average is equal to IO, which comes by applying KCL at this node. Since the capacitor current average value is 0, ID1 average is simply the IO average. So that is what is shown here. So the inductor current average waveform value which you are looking for is nothing but IN plus IO, and that is indicated by this dotted line. The next waveform is that of the switch current IS1, and since the switch is directly in series with the input voltage source, it is also same as the input current IN. So this wave shape IS1 or IN is exactly same as the inductor current waveform during the on interval when the switch S1 is conducting, and during the off interval when S1 is off, the current is 0 as shown here. Now if you want the average value of IN or IS1, we can obtain that by power balance. So IN is essentially d over 1 minus d times IO, which we derived earlier from the power balance equation, and that is indicated by this dotted line. And we can also use this power balance expression for IN to get another expression for IL. So essentially IL bar is IN plus IO. Substitute IN equals this value in this expression. We can see that IL bar is also IO over 1 minus d. And in a buck boost converter corresponding to the buck mode of operation with d less than 0.5, the input current is less than the load current IO. The next waveform is that of the diode current ID1. So once again, the diode current is exactly same as the inductor current during the off interval when the diode is conducting, and during the on interval when S1 is on, the diode is reverse biased and there is no current. So on interval it is 0, off interval is same as the inductor current waveform. We can also get the average value of ID1 essentially by applying KCL at this node, average KCL at this node. So IC bar is 0, therefore ID1, which is IC bar plus IO, is simply IO, which is indicated by this dotted line. Finally, the last waveform is that of the capacitor current IC, and the direction has been denoted by going from bottom to the top. So during the on interval, the capacitor is supplying the load current, so it is discharging. It's a negative current of value equal to minus IO. And during the off interval, the inductor current flows in this direction. So IC would be IL minus IO during this interval. Essentially in steady state, IC also has to be equal to 0. IC bar is equal to 0. A similar set of waveforms can also be obtained for the boost mode of operation for d greater than 0.5. So here is the Vn waveform, and for boost mode of operation, clearly VO has to be higher than Vn as indicated here. VL is a similar square waveform, but now the VO magnitude is higher, and the DTS interval is longer than the 1 minus DTS interval. IL is a similar wave shape, with the slopes being equal to VL over L in the corresponding subintervals, and the average value is still IN plus IO. IS1, same as the inductor current during the on interval. ID1, same as the inductor current during the off interval, with its average being equal to the load current. Now, in a boost mode of operation, IN, the input current, is always higher than the load current. IC is IO minus IO during the on interval, and it is IL minus IO instantaneously during the off interval, with the IC average being equal to 0 again.